Assalamualaikum warahmatullahi wabarakatuh. Selamat sejahtera. My name is Muhammad Nur Hakim bin Nudin. My metric number is CE190102. Okay, let's get started. I will present about our group members. The project is performance of cache memory by using ParaCache simulator. This is we are from section 1 and group 8. The group members is first Leong Chisam, second Muhammad Amirul Aiman bin Abdul Aziz, and third is me, Muhammad Hakim bin Nudin. Let's proceed to introduction. In introduction, I will talk about 4 things, that is cache memory, project details, method of replacement, and write policy. For the cache memory is a type of memory that operates at a very high speed. It is used to boost performance and synchronize with a high-speed CPU. Cache memory is more expensive than main memory and disk memory, but costs less than CPU registers. CPU stands for Central Processing Unit. Next, a form of memory that functions as a buffer between RAM and the CPU and is incredibly fast. Cache memory stores frequently requested data and instructions so that the CPU may access them quickly when needed. Cache memory is used to reduce the average time it takes to access data from the main memory. Lastly, the cache memory, the cache is a smaller and quicker memory that holds copies of data from frequently accessed main memory locations. So we proceed to project details. Our project details, we will utilize ParaCache simulation to test the performance of cache memory in this project. The hit or miss rate of a memory cache will be tested in the simulation by using 2 methods of cache mapping, which are direct mapping and set associative mapping. The goal of the study is to determine how well a cache performs. So the memory size, cache size, and the given instruction to the cache will all remain unchanged. Next, I'm talking about method of replacement. So for the method, we use first come first serve (FCFS) because it's an operating system student algorithm that executes queue requests and process in the order in which they were received. For the last instruction and for the last introduction is write policy. We use write back policy because write back policy only writes cache updates and consume less memory bandwidth and power. Also, both valid and update cache control bits are necessary. Lastly, only one writing to memory is required for repeated writes to a cache block. This is the flowchart for the write back policy.
Hello, my name is Leong Chisam, matrix number CE3000193. So I'll be doing the demonstration for the ParaCache simulator on direct map cache. So the value that we choose is 16 for the size cache, memory size is 256 and offset bit is 2. So okay, here offset bit is 2. So index is the cache size. So the way we get 2 bit here is 16 divided by 4 because we are at index size here. So index is also called the block. So in a line of memory block we have 4 bits, so that's why 16 divided by 4, and then we need to do the log base 2, so we get 2 bit, and then 256 is the total memory size. So 2 power of 8 equal to 256, so that means that the memory size is 8 bit. The maximum size we can get is 8 bit. So to get the tag here, we can use the formula, the memory size minus the index size minus the off bit size, so we'll get 4 bit. So right now I will generate 10 random instruction right here. So all of the instruction is in a hexadecimal format. Then submit. Next, so the dB in hexa will be converted into the decimal. So dB equal to 1101.1011. So as we can see here, the total is 8 bit because of our memory size is 256, which is equal to 8 bit. The maximum size we can have is 8 bit. Let's say the hexa here is dB right now, dB 1101.1011. So the way how it is divided here is, so 4 bit here for the tag, so the leftmost 4 bit is for the tag, and then offset bit is 2 for the rightmost, so this is for the offset, and then the last middle 2 bit here is for the block or the index. So since the index is 110, 110 is equal to 2, so 0 is equal to 0 0, 1 is 0 1, 2 is 1 0, and 3 is 1 1. So this is the index 1 0, so we look at the index 2. Okay, so next we can look at the valid bit. Valid bit is 0 bit, so valid equal to 0 bit means there haven't been any data stored in the cache table. So next, since there is no data previously loaded into the cache table, it is a miscache, and then the value of the tag bit will be loaded into the cache, and also the data from the memory block will be loaded here. Next, load the hexadecimal A, which is equal to decimal 10. Oops. Next, 1 0, we look at index 2. So the valid bit here is 1 right now, means there is already data here in this line. So if the valid bit is 1, we need to look at the tag. So we need to compare the tag value, tag in the cache table and the tag in the load instruction. So compare it, 1101 compare with 000, it is not a match, so it will be a cache miss. And then a new block memory will be stored in here. We will replace the previous block. Next, so it's block 2. Next, so load 6A. Okay, same, because of the index is 1 0, we look at the index 2, and then valid bit is 1, we can compare the tag. So the tag is different, so it is another miscache. And then the bit is 0, we load the new block here. So 6A is equal to 6A is equal to decimal number 106. So 106 divided by 4, you get 26. And 1A block here, 1A means 26 decimal. So that is why we choose block 1A, because of the hexadecimal 6A. Okay, next, 3C, convert into binary. And then the index is 1 1, so we look at the index 3, this whole line. So valid bit is 0, that's means another miscache, because there's no data previously loaded here, so there will be data loaded here now. So the tag 0011 will be loaded into index 3, and the hexadecimal 3C from the memory block will be loaded here. So block F is chose because the hexadecimal 3C. So 3C convert is 60 divided by 4 is 15. So 15 in hexa also mean F. Next, load FC. So index is 1 1. So look at the index tree. So the value bit is 1 means there is data here previously. So if the value bit is 1, we can compare the tag. 0011 and 1111, it is not the same, so it is a miscatch. And then the new data and then the new tag from the instruction will be loaded into this index line. Next, okay. Next, we got another instruction. So index is 10. Look at the index 2. But bit is 1, we can compare the tag. So the tag is different, 0110 and 0010, a miscatch. New data will be loaded into the tag, which is 0010 will be loaded here. And the data from the hexa from the memory block will be loaded here. So another index 2, value bit is 1, we compare the tag. Another miss, the data will be loaded into the cache table. Submit another, okay. So index bit is 01 right now. So we need to look at index 1. So since the valid bit is 0, means there's no data loaded here previously, and it will be a miscatch. And then the tag bit loaded here, and then memory block from block 39 will be loaded here because of A6. 75. So 75 equal to 0111 0101, and then look at index 1. Whatever is 1, we compare the tag. So another base here will be replaced by the new tag and the new data. Next, submit. Is index 3, valid 1, we compare the tag. Tag is not matched, so it is a miscatch, and the new tag and the new data will be replaced here. So we have complete all of the 10 instructions. So the statistic is we have loaded 10 instructions. All of the instruction is missed, so let's do another one so we can look at the hit catch. So let's say I want to load 1C again. Submit. So 11, look at index 3. Whether bit is 1, we need to look at the tag, compare the tag. So the tag is match 0001 0001. It is a hit catch. And then also the data will be loaded here, which is the same, and then the same memory block. So as a result, 11 instruction has been loaded here, and only one instruction hit. So the hit rate is 9%, and the miss rate is 91%. So we can say that indirect mapping memory block, so it's assigned to a specific line in the cache table. If the value bit is 0, there is no data. So value bit is 1, there's data, and we need to compare the tag. If the tag is matched with the instruction tag, so it is a hit catch. Thank you.
Assalamualaikum and hi, my name is Muhammad Amirul Aiman bin Abdul Aziz, numeric CE200209. Now I will represent about how the process cache work at these three main elements which implement the processor, cache and main memory. This is figure of how cache process in the share the data and instruction. This called share data because we can see at this block it share instruction and data to transfer and go back from processor to cache. From processor, we know that it have a register that may hold instruction data and storage of address. Process of cache occur when address in register will transfer into the block cache. This part of compare that my friend has been explained how it will compare, that if cache is value is same in 1 and tag value is same as before data, it will declare as hit rate and copy the new data into our cache table and put block memory data in cache table also, that we have been used in the simulator to instruct this project. When cache is value is 0 or value of tag is not same as value yet, it will declare as misread and insert the block memory data into cache table. That's how it will compare. Now let's move to the another slide, which this is our process cache work in separate of data and instruction. When these two physically separate parts, where one part called the instruction cache and that dedicated for holding instruction, for the other is called the data cache, which is dedicated for the holding data. At this is same as before block diagram of share data and instruction, but in this separate into two blocks. Both of the instruction cache and data cache are logically considered to be a single cache, described as a split cache because both are hardware managed cache for same physical memory hierarchy. And then for next, this is read hit in the process cache, working which for read hit data requested by the processor during a read and write operation is available in the data in the cache. Read hit happen when data available to cache and send back to our processor. From this I will show how data read hit will happen, which is from this, if the data requested is available or valid, it will transfer to cache and straight away to our processor. And then back to our slide. For read miss, data request from processor is not available in the cache. Read miss will happen when data not available to cache and send back to memory, to cache and insert to our processor. Now I will show read miss will happen in this. From this processor, if data request is not available or not valid, it will go back to our main memory, and after that transfer to cache and insert to our processor back. After that, back to our slide. For write cache, for miss and hit, it's same way as read cache process. That's all for me, and thanks.
For our recommendation is to increase the cache block size. This is because by increasing the cache block size is the simplest technique to reduce the miss rate. It also improves the miss rate by following to the principle of locality. Lastly, it will help with spatial locality. That's all from our group. Thank you.